All right, now we're looking at pendulums. And so this is when you've got something hanging from a string, you've got a mass hanging from a string, and kind of what's going on with it. So for a pendulum, the restoring force is a little more complicated. So what I want you to do is imagine you've got a pendulum and it's going to be swung out to one side. What you've got here, if this is the neutral position, then this right here is some angle theta. And we can draw a free body diagram for that pendulum. You're going to have F tension pulling kind of upwards diagonally. You're going to have Fg pulling down. And that means we can break this Fg into two components. One component is pointed kind of in the direction towards the center. The other component's kind of opposing Ft. Since the Ft component will cancel, or the component right here is going to cancel with the Ft, we kind of ignore it because they end up canceling out. And we're left with this force right here. And what that force is Fg sine theta. But it's in the negative direction from our theta, so we put a negative on there. So the restoring force is technically negative Fg sine theta. And you'll notice that this is a restoring force because it's negative and it opposes the direction that you've moved, sine theta. Now we can simplify that for small theta. The force is equal to Fg theta, negative Fg theta. Because and you can try this on your calculator, just plug in some numbers real quick. If you have a really small angle, theta and sine of theta are basically the same. And if you think about it, it kind of makes sense, because if you think about the beginning of a sine curve, it's sort of increasing at a slope of roughly 1. And then it continues. So if we're dealing with just this kind of first section here, which is all of what we're going to primarily deal with, then you can simplify it as this Fg theta. You don't really need to know this for the AP test, but it's something that it's called the small angle approximation that will come up in later physics courses if you take more physics. I just wanted to introduce that idea here. Regardless, the period ends up being calculated as t equals 2 pi times the square root of L over G, where L is the length of the pendulum. And just like with the spring, I'm not going to go through the derivation here. If you want to talk through that with me, let me know and I'm happy to do it. But for the sake of this class, we just need to be aware of the results. And so to save time, I'm going to skip that unless you're particularly interested. But we can talk about why this sort of intuitively at least seems reasonable. So if you think about a longer pendulum, that means that the end of the pendulum has farther to move for the same given angles, right? A really long pendulum has a far distance to move. So if L is larger, we'd expect T to be larger. On the flip side, gravity is the thing pulling it towards the center, right? You've got this Fg here. So if Fg is bigger, then you'd expect it pulled more tightly towards the center, and so the period would be shorter. It basically gets restored faster. So this kind of intuitively can at least seem reasonable from that, hopefully. And the gravity, or the energy here, is just using delta Ug equals mg delta H, which can also be written as delta H will be, what would it be? If we have theta, it's going to be L minus, just trying to do that geometry in my head, L minus cosine theta. L minus L cosine theta. And that's because I should have just drawn this out. We have our pendulum swing. This is L. This is L. This whole distance is L. And then this distance in here is L cosine theta. And this distance down here is my delta H. So L minus L cosine theta is my delta H. So you could also write this if you wanted as mgl times 1 minus cosine theta. All right, if we want to analyze it, it's almost completely identical to the spring, which is why I just copy-pasted this from the previous slide. So if you want to talk about some of the details, you can go back to that. But the difference is, instead of delta x, we're going to have theta. You could also put in delta h if you wanted. They should be pretty similar. And instead of displacement in x, we're talking about displacement in theta. So this, again, F is equal to negative FG theta, but it's still going to be maximized when the theta is maximized. Kinetic energy is completely the same, but then instead of US, we're going to have UG is equal to mg H, which is also, like we had just derived, mgl times 1 minus cosine theta. So again, the idea behind these is not so much that you know all the details, but that you can do this kind of reasoning. You can imagine as it swings back and forth, well, at the ends, it's momentarily stationary, and so at those two endpoints, there's no kinetic energy. When it gets to the middle, it's at the lowest height, so we know that it's lost the most gravitational potential energy, so it's going to have the most kinetic energy. And this is just the kind of reasoning that you've got to be comfortable with for analyzing the motion. Otherwise, it would just be, if you increase the length of the pendulum, what happens to the period and questions like that. Once we get into some of these questions, you'll see that it's all, I think, pretty straightforward, but that's the idea behind pendulums.